This is an ESP32, a chip that costs about $8, and people usually buy it to do boring little jobs like blink a light or read a temperature for a project out in the garage. But someone just got a real language model running on one with absolutely nothing connected, meaning no server and no account. And it just sits there, writing stories faster than you could read them out loud. That chip only has half a megabyte of memory, which is less than a single photo off your phone. So how does a language model actually fit in there? When people say this chip has almost no memory, they mean the fast memory, where the actual thinking happens. But look at the standard ESP32 S3 development board that anyone can buy on Amazon for about $8. You'll see it actually has 3 separate places to put data. You have that tiny half megabyte of fast memory right next to the processor. But you also get 8 megabytes of slower memory, plus 16 megabytes of basic storage built into the board where things just sit when the power is off. Only the fast memory is built for the math a neural network does, because stepping out to the slower memory or the storage costs time. It is like trying to cook dinner when your ingredients are locked in a shed across the yard. So once you're actually trying to run something in it, that half megabyte of fast working space gets eaten up almost immediately. And that leaves you looking at those 3 different buckets and wondering, which of those spaces does a language model actually need to live in, and exactly how much of it? Right now, this language model runs locally on ESP32 S3 hardware, carrying 28.9 million parameters, which are just the tiny mathematical weights that hold all of its knowledge. Until recently, the absolute ceiling for what anyone had managed to cram into this kind of space was a brilliant project by a developer named Dave Bennett. It maxed out at 260,000. That makes this jump over 100 times bigger on the exact same physical constraints. It's like finding out that the little chip you bought for about $8 to blink a light or read a temperature sensor is secretly writing a novel on its lunch break. And it makes the whole thing hard to explain, because even if you accept that the code is efficient, you're still staring at a chip with half a megabyte of fast working space, and you still have to answer where exactly 29 million of anything physically go on a board this cheap. The developer posted this exact breakdown on Reddit, explaining that you have to aggressively squash the parameters down to 4 bits. But it turns out that even after that extreme compression, the model still weighs about 14.9 megabytes as a physical file. Because the board has 16 megabytes of storage, the file only just fits on the thing at all. But a processor can't do math out of cold storage because that connection is painfully slow. So to actually run the program and generate a story, the data has to be pulled into the fast memory first. The problem is that the file is roughly 30 times larger than the working space the chip actually has. There's physically no way the entire thing is loaded at once, which leaves you staring at a pretty glaring gap in the math. If the file is 30 times too big for the room it has to work in, what exactly is sitting in the fast memory while the chip is writing a word? To figure out what is actually sitting in the fast memory, you have to look at what those 28.9 million parameters are actually doing, because the vast majority of them aren't doing math. Out of the whole pile, roughly 25 million of them make up a lookup table that the chip only ever reads from and never calculates with, which is essentially just a dictionary mapping words to numbers. And because it's just a static reference list, it doesn't need to be in the fast memory at all. That chunk of the file just stays parked right where it is in the slow storage, which is perfectly fine because you wouldn't load an entire phone book into your brain just to call a plumber. Instead, when the chip needs a word, it just looks the word up. According to what Circuit Digest is reporting, for every word the runtime spits out, it only fetches a handful of rows, give or take a few hundred bytes, from the storage into the fast memory. So the only piece of the model that has to live in that tiny half megabyte workspace full time is the much smaller chunk of logic that actually does the thinking. Which solves the space problem, but creates a glaring mechanical one, because reading from standard storage is slow. So if this chip is constantly running out to the shelf to fetch numbers for every single word it writes, why doesn't that wreck the speed? If you're assuming that treating storage like active memory would tank the speed, you're in good company. But the project's own performance log shows the penalty for pulling numbers off the slow shelf is so tiny they call the flash bandwidth nearly free. That means reading from storage barely costs anything. They actually measured the memory trick against a standard version of the model without it, and the new approach consistently beats baseline across multiple training runs. And if you're wondering if the math turns into garbage when you crush the weights down to 4 bits so they don't spill off the board, the project records the whole squashed pipeline as validated end-to-end. That confirms the trick as a sound piece of engineering that proves the approach holds up under measurement. So the storage trick explains how a heavy model physically fits on an $8 microchip. But it still leaves us with a problem, because it fails to explain how something this small can write coherent English at all. So this clever little workaround was actually borrowed from some of the heaviest hitters in the industry. The technique was originally built by Google for their Gemma models, where the goal was exactly the same, keeping an AI from swallowing every megabyte of fast memory on your phone. In that world, it has a formal name, Per-Layer Embeddings, which Circuit Digest specifically credits as the mechanic borrowed here. And the distance traveled is the impressive part, because taking an architecture designed to save space on a smartphone and dragging it down to a hobby board that costs about $8 is great engineering. So the storage trick explains how a giant lookup table physically fits on a cheap little microchip. But that leaves us staring at a harder problem, because if the storage half of this was borrowed from somewhere else, what's the software actually running the model on the chip itself? Well, just like the storage trick, the engine actually running the math is a public project called Llama2.c that sits at around 20,000 stars. That means it's a heavily traveled piece of software. The reason it can actually work on a chip this small is right there in the description, which calls it inference for Llama 2 in one file of pure C. There's no Python anywhere in this thing, and there's no giant machine learning framework running underneath it trying to manage the memory for you. It's just plain C code, executing the math directly, which is exactly how you squeeze an entire AI runtime into a space smaller than a nostalgic MP3 file. So if you step back and put the pieces together, both halves of this build were actually assembled from existing proven parts. But that leaves us staring at a real Llama 2 LLM architecture running on a chip this cheap. What on earth do you actually teach a language model that small? So if you want a brain that small to actually work, you have to shrink the universe it lives in. That is why this model was trained exclusively on a dataset called TinyStories. And TinyStories is exactly what it sounds like. A collection of synthetic children's stories written with a vocabulary of only a couple of thousand basic words. That makes it perfect for a piece of hardware that usually spends its days blinking an LED. It was originally put together by Microsoft Research back in 2023 to answer one very specific question. That was literally just, how small can language models be and still speak coherent English? Because it turns out that if you drop the complexity of the language down to the absolute floor, a model can hold a basic story together at only a few million parameters. That is the exact finding this whole $8 hardware project rests on. So the clever memory trick we talked about earlier is what got the model physically onto the board. But this heavily restricted dataset is the only reason a model this small actually has anything to say. So which is the real achievement here? Is it the sheer hardware engineering to squeeze a language model onto a chip this cheap, or the dataset that made the model's job small enough to be possible? So when you actually fire up this board that costs about $8, the catch is that the output is entirely dictated by that TinyStories dataset. What you've effectively built is a dedicated bedtime story generator. It outputs short, simple children's fiction, churning out roughly 9.5 tokens per second. That is a pace faster than you could comfortably read aloud. The model has no concept of what a question is or how to answer one. Whatever comes out of the chip is just going to be more fiction, simply because a story is the only structure it was ever taught to produce. Remember, this board was built by Espressif to sit inside small connected gadgets and handle their Wi-Fi. That is a day job that has exactly nothing to do with generating paragraphs of English. So while it's true that this setup can write a coherent story about a cat, it leaves you wondering if this memory trick could actually survive being asked to do a real job on a real product. So if you wanted to take this whole setup and bolt it into a piece of hardware you could actually sell, what is that half a megabyte of fast memory competing with? Running this project on a bare chip on your desk is one thing, but in a real gadget, that space is basically a violently overbooked flight. An industry breakdown from NeedCode points out that a standard half a megabyte microcontroller is already sitting exactly at the ceiling. You hit that limit once you combine a basic wireless radio stack with a small model running on the device itself. And that calculation is just the baseline to get the chip talking to the outside world. That means it completely ignores the memory you would need for the product's actual application code or combining readings from more than one sensor. It also leaves out the ability to download an update over the air without bricking itself. You can't exactly sell a smart thermostat that forgets how to read the temperature because it's too busy using all its available brain power to write a bedtime story. The real constraint on a shipping product is that the model has to share that fast memory with the software doing the actual job. The room this project used so freely is room a commercial device simply does not have spare. That leaves you looking at a brilliant piece of engineering and wondering if a setup like this is actually worth having in the first place. So the answer to how a language model actually fits into half a megabyte of memory is two things at once. The storage trick keeps the lookup table safely out of the fast memory, and the task itself was deliberately shrunk down to writing basic children's stories. That storage trick is the durable part, which you can go verify yourself for about $8. The project's own results log marks the approach as validated end-to-end. It even claims the setup beats baseline runs, largely because pulling those specific rows out of storage is nearly free. But that brings us back to whether any of this is actually worth having. Combining a Bluetooth stack and readings from more than one sensor puts a standard chip right at the ceiling. That means the room this project used so freely just isn't there in production. And even if you had the space, the part that does the thinking spends all its free time writing toddler fiction at roughly 9.5 tokens per second. That isn't exactly going to operate your smart toaster. So the memory problem, which everyone assumed was the blocker for local AI on cheap hardware, is solved and the code is public. The wall just moved. The real limit now is leaving enough space on the chip for the rest of the device to exist while figuring out what a model this tiny is actually good for. Anyways, that's all folks.